Thank you. So thank you for the kind introduction. I will quickly share my screen. Okay. Please let me know if it is visible for everybody.
Yeah, we can see it. If you can move to a full screen, it will be better.
Yes. Okay, then.
Good. Excellent.
Hi, everyone. Good morning, good afternoon, or good evening. And thank you, Professor Avi and Professor Shivam, for this kind invitation to speak on this platform once again this year. It was great to hear such intuitive talks from yesterday and also from today. I am Ritu-Ranjan Srivastwa, and I would like to take this opportunity to present to you all our ongoing research on detecting fault injection attacks using machine learning and digital sensors, fusion, and leveraging the fast prototyping abilities of high-level synthesis for the evaluation. So we will be going through an introduction to this work and see the motivation behind doing this research, and then we are going to talk a little bit about the relationship between standards and machine learning implementation on hardware. Finally, we will hover through the concept of using machine learning for fault injection detection, and then discussing a little bit about the methodology of our approach, followed by the results at the software level. And then we will see how we can use the high-level synthesis for custom prototyping and testing of the custom machine learning models on hardware for inferencing. And then finally, we will see how we can progress on this direction, and what are the next steps that we are following. So as we are all aware of the increasing number of devices and the edge getting more powerful to have processing capabilities of heavy data from real-time sources. And it is bringing with us more scary circumstances. The more sophisticated we make the devices, the more we risk increasing the vulnerabilities to them from multiple attack surfaces. So whilst we have classical protections which are reactive in nature, these are not equipped to handle such sophisticated attacks that exist as of now, and which are ever evolving. So therefore, what we need is to increase the countermeasures too in the same magnitude as these attacks. And while we can place a lot of different types of sensors around our devices, it is pertinent that we also have a smart solution to really infer the accurate outcome and handle all those inputs. Since the amount of data being handled by these devices is getting bigger and bigger, so we need a method to handle such large volumes of data. And what is better than at handling big data than our good old machine learning techniques? So we need a solution which is generic in nature, and it covers a panorama of attacks and is of course trustworthy and robust. All right. So the motivation behind this work is of course to make the devices, it seems to be some kind of issue. Yes, sorry. So yeah, so the motivation behind this work is, of course, to make the devices more and more secure, because with the current culture of the semiconductor industry, where several critical steps are outsourced, such as the fabrication and also testing in some cases. So we are risking our designs to get infected or stolen and reverse engineered, and not just for the purpose of overproduction, but also for the attacks. So it becomes easier to pinpoint an attack once you know the design, which in other words makes it a white box attack. So while obviously it is not possible at this point to reverse this culture and have all the design processes to be done in-house or in trusted locations, but what is possible is to create a more robust functioning or a more robust reactive countermeasure solutions that can counter unknown circumstances, such as attacks that can affect the overall functioning of the system. So, well, however, it is important to identify the exact parameters which can be affected in insecure locations by adversaries, and how exactly to protect those parameters. Which is why we need a solution that is highly accurate and can uncover even the tiniest of modifications in the design or in the functionality of the chip. So we also need a sustainable solution, and machine learning seems to adapt to growing data. So in fact, the more examples we have for machine learning, the better the accuracy is. And with better engineering, it can perform excellent pattern recognition from behavioral data, and the proof of which is already in the literature. Why this is so important? Because these threats have repercussions in multiple market segments, such as autonomous transportation, consumer electronics, and even healthcare. Well, a little bit talking out of scope of the defensive application in detecting fault attacks here. So while thinking of the safety implications in automotive, for instance, we can think of the ISO 26262, the functional safety of road vehicles standard. And with the upcoming autonomous cars, which are equipped with advanced AI capabilities, we need to stay, we need safety assurances to follow the 26262 requirements, which basically is not built with the scope of autonomous vehicles. So these detection methodologies can provide some quantitative metrics for evaluation, and based on which we can decide upon the safety assurance or integrity levels. And similarly, if we opt for a common criteria certification, it is required in the EVA VAN 4 that the vulnerabilities to the TOE, the target of execution, should not be exploitable. So the detection capabilities, once again, can provide some assurance on security and can help ensure conformity to the standard. And while talking a little bit about the safety of the AI implementation itself, there are also efforts being put in this direction by international committees, such as the ISO-IEC Joint Technical Committee 1, Subcommittee 42, which is focused on producing standards in the area of AI. More about this in the end of this talk. So moving on. Coming back to the detecting fault attacks, so we have already seen several results of using machine learning in side channel analysis with a higher accuracy. And there are also some works about using machine learning for fault attack analysis. However, most of these works are roughly based on the analysis and not on the active on-chip detection of the fault attacks. So it's mostly like a passive analysis. And it is not as like on-chip detection as a reactive defense approach, which is live with the user logic. So what we need is a solution that is aware of the normal behavior and functionality of the chip, and is aware of the adversarial settings and conditions such that any disturbance in the functioning of the chip is detected with a minimum false positive or false negative rate. And it is expected to extrapolate the adversarial behavior to identify unknown attacks and thereby work as an immune system of the device. So what we do is that we have collected a bunch of data by performing clock glitch fault injection, electromagnetic fault injection, laser fault injection, and temperature and voltage fault injections in multiple different settings. And what we are doing is we are using that to train our machine learning model against the normal chip behavior. So the idea is basically to train a model which is able to precisely classify between a normal behavior of the chip and an attack situation, and then try to detect an intrusion as early as possible, ideally before the harm is done. Since we are using digital sensors to achieve that, and we rely on the linear saturation of the sensors to provide us with an insight of when an attack is initiated. So using this information, the model should be able to predict multiple types of fault attacks and not just one, and then also try to predict the type of attack if possible, for a precise fail-safe mechanism to be activated. So the idea is to keep the detection fast, and therefore we break the process into two stages. The first stage performs the detection of the attack, basically the presence of the attack, and that is irrespective of what the source is. And then once the attack is detected, it would try to predict the type of perturbation. So we are also building a catalog of such machine learning detection IPs with different features such as footprint for power, efficiency, latency, etc., to be selected from, and based on the resources available with the device. So you can choose one from this list. So we use HLS framework for achieving this as of now. The next big challenge then is to protect the machine learning detection IP itself from being the target, and for which we are also working and in securing it in the best possible way to provide protection against adversarial impacts and tampering. More about this towards the end of the slides. So now for the purpose of sensing, as I mentioned, so we are using a fleet of digital sensors, which provide us with the continuous status information, which is aggregated, and then it is fed as input to the machine learning models. The resolution of the digital sensors can be set based on the requirement, for example, 32 bits or 64 bits. In the example figure here, you can see it's 64 bits. And these are compact and tiny and are fused with the user logic, and hence it's hard to locate. And since they are operating in parallel with the user logic, it is also hard to locate them time-wise. So digital sensors are agnostic with respect to the attack source, but also that they can convey informative inputs for a final classification of the attacks of the attack vector, basically. And you can notice that such capability to analyze the attack, it requires the sensors to output not only one bit, but a bit vector, basically. So which can be interpreted as the status of the sensor. And the aggregation of multiple statuses is known as the smart monitoring, what we call it. And a smart attacker still can find a configuration of the induced stresses whereby it is not detectable by the sensors. What we can call it as a blind spots. So this is the reason why the sensors can be either spread across the chip or can be clustered around the sensitive IPs, so that any tampering or any attack which is targeted to those critical security parameters can be easily detected by the sensors. So building idea discussed in the previous slide. So what we do is spread the digital sensors across the chip while considering the entire chip as sensitive. And for the pre-processing part, what we do is collect all the statuses from the sensors in a buffer, which the length of which is depends on the user. And this collection of the buffer data is from each sensor. And what we do is we club them together into a linear vector before feeding it to the model for the detection purpose. So the inherent latency comes with this method is the time that it takes to fill the buffer for the first time. So we need to make sure like the choice of the buffer depth is as allowed by the requirements for the specific use case. So the bigger the buffer, the better the detection, but it comes with a cost of latency. But that is just for the first time when it is filled. After that, it works like a FIFO queue. So an example configuration is shown in the left figure of the screen, and in the right figure is a flowchart of the working of the system. At boot up, the sensor data is collected from the buffer and is passed on to the stage 1 detection, which is basically checking if the statuses reveal any presence of attack. So if there is no attack detected, it continues with the process. And in case an attack is detected, the next stage is activated, which then tries to predict the type of perturbation. For instance, if it is originating from a clock glitch fault attack, fault injection attempt, or electromagnetic fault injection attempt. So this step is optional, as it is just for the forensics purpose and can be left at the discretion of the designer. But if it identifies an attack type, then the output of this stage can be used to trigger specific fail-safe mechanisms by the lifecycle management of the system, for instance, like halting the operation or key zeroization, etc. Well, the problem of detecting fault injection and classifying it against normal chip behavior is a classic case of binary classification. In order to come to a conclusion of the choice of the machine learning model, we indeed need to constantly upgrade the model. However, to begin with, what we can do is list down all the algorithms that can be used to perform the classification task and test their efficiency on the collected data to get an initial ranking of all the algorithms by giving them scores for their different detection capabilities. So we have to do this like empirically. So for this ranking, the tests for each algorithm can be done by running binary classification between the individual attack class and the nominal class, and then running a classification between different fault injection classes itself. So this step would be helpful in identifying the candidate for the second stage. And finally, for the highest score, evaluating the performance of the algorithm by running a classification between a combined set of all the attack data sets and then the nominal class. So with all these scores, the final ranking can be done. And the next step then would be to dive into the complexity of each of the algorithm to calculate the throughput. So all this information is cataloged and can be used to decide which algorithm to be used based on the use case. From this, you may also come to a conclusion that the classification between the attack classes and the nominal class can also be modeled into an outlier detection or one class classification problem. And we will we will discuss about this later in the presentation. But looking at some of the results, which is from an evaluation which was done using just the electromagnetic and clock glitch fault injection data sets. From the catalog of algorithms, we selected the Gaussian naive Bayes classifier for this evaluation. And some of the results are presented on this slide. So it is clear that at individual detection of single attack source, the accuracy is quite high, and even 100% in case of the clock glitch fault injection attack. But the accuracy falls down when it comes when we combine the data sets. However, it is to be noted that the naive Bayes is a linear model, and the accuracy will go up if a more dense like nonlinear classifier is used instead. And finally, the perturbation type detection, it gives an accuracy of 77%. In correctly identifying the different attack sources, but 23% of the time electromagnetic fault injection attack is predicted as a clock glitch fault attack. So this is due to the insufficient resolution on the sensors. So for instance, we have used 16 digital sensors for this evaluation, with each sensor having a 32-bit resolution and a buffer length of 13. And the results can be improved if we increase the resolution of the sensors, for instance, from 32-bit to 64-bit, and also increase the number of sensors on the chip. So it gives more feature in the data and more resolution to differentiate between different perturbation types. And of course, improving the machine learning algorithm using a more deep neural network would be a better option. So to test the performance on hardware and replicate the results, we utilize high-level synthesis. The framework is composed of various stages and can be understood from this list. Firstly, the training is carried out to train the machine learning model parameters using standard software machine learning frameworks in any high-level language, for example, Python, after which the trained parameters are extracted. Then a C or C++ implementation or design is created from scratch with no external library support. And the machine learning inference model is initialized with the learned parameters extracted at the previous step. The C source, along with the test bench, which is also written in C, to validate the design performance at the simulation level is used to perform the high-level synthesis using the Vivado HLS design platform to generate the RTL without any optimization, other than the generated HDL, which is, what Vivado does by itself in the design flow. So we don't have any control upon the generated RTL code structure. So the generated RTL is then packed into an IP and then imported in the Vivado HLX suite, where a controller program is written in Verilog to interface with the IP. And the test data set is stored for the machine learning IP in a RAM block, block RAM, which is used by the controller program to segment and test the IP for classification accuracy. So this the steps can be visualized from this slide. A database of the machine learning parameters is created based on the catalog generated earlier. And these parameters are used to model the selected algorithm in C, including a benchmark to test, and then the high-level synthesis tool works its magic to synthesize the RTL. And then we can generate the IP catalog of all the algorithms with a generic interface and ready to use for the target use case. So the usability of this is in creating an off-the-shelf catalog of IPs that are tested and benchmarked for accuracy, footprint, latency, and so on. So it is to be noted that using high-level synthesis comes at its costs. First of all, the code might not be optimized for performance as per the requirements. And there are specific guidelines that can be actually followed using to optimize, such as the Xilinx HLS optimization guide that provides an extensive list of parameters to optimize the RTL output. Therefore, it is advisable to use high-level synthesis for establishing just a proof of concept and rapid prototyping. But the advantage of this is that it is very fast and it simplifies the EDA process for the user. The image is that of the target board, and it captures the information that I provided in the earlier slides for the version of the experiments that we performed with the 16 32-bit digital sensors on the clock glitch and electromagnetic fault injection datasets. So for someone who is interested in the high-level synthesis, it is important to study about the various optimization strategies for having a sustainable development process. And if you're going to use a custom framework using a generic high-level synthesis tools such as Xilinx Vivado, then optimization can be done, using the HLS optimization guides, where you can use pragmas or by using design strategies to optimize the source code directly. And Vivado HLS provides some pragmas that can be used to optimize the design, which can reduce the latency, improve throughput performance, and it can reduce the area as well, and the device resource utilization, which can of the resulting the RTL code. So these pragmas can be added directly to the source code for the kernel. There are several other features that can also be used for this purpose. Another approach is to directly use the Xilinx Vitis AI tool, which is an advanced tool built with optimized machine learning high-level synthesis, and it is also supporting various machine learning frameworks such as TensorFlow and PyTorch. It also provides various pre-optimized models if your target device is from Xilinx, and one can use these models to retrain based on the use case. As I mentioned earlier, that we need to have the first stage of the detection to have higher throughput, and the second stage to have higher accuracy. Because in the first stage, the detection is simpler, because you have to detect from all the attacks and the normal behavior of the chip. So it is a simple detection scenario, and it gets very complex to detect in the second stage, because you have to then because there are different attack data sets, and you have to basically, if we see the linear saturation of the digital sensors, so it leaves with a very less resolution and less number of features to identify from the resulting attack data sets to classify exactly which classes they belong to. So, so the approach can be like of an hybrid model, where there can be a simpler model with high accuracy from the catalog of algorithms working for the stage one, and the complex deep neural networks in the second stage. This can also be motivation for the research in this direction. And so, as I mentioned a few slides back about the approach of outlier detection method that is synonymous to detecting multi-source attack against normal chip behavior. So here is some details of that evaluation. So in the last year's workshop, we presented our results of hardware Trojan detection using outlier or one-class classification methodology, which was very promising, and we got some publications out of it. What we are doing currently also is to do the same thing with the fault injection detection. So the methodology for this would be somewhat similar, and we first compute the t-test coefficients for the nominal case, which is the standard chip behavior, and then train the outlier machine learning model with these coefficients. And then after, when it is placed in an adversarial environment, and when some unknown state information is received, the corresponding t-test coefficients are computed again from these statuses, and then the model predicts whether it is an inlier or an outlier. Also, we found out that the t-tests work only with the normal distribution of data. So what we are dealing with is not normal distribution, and we are also evaluating it using KS test, which works better than the t-test for most cases. And for both the hybrid two-stage detection and the outlier detection works, we have been evaluating, and the work is still in progress, and we will be publishing the results soon. So another important aspect is to standardize the development, testing, and verification of machine learning implementation on hardware. So once the framework is standardized, it will be easier to perform the validation and quality control with the policies. So this is especially important when we think of the defensive machine learning model as the target of the attack. So apart from fault injection, there are many other existing attacks that target machine learning implementations in hardware, such as model stealing, where an attack is used to reverse engineer the neural network models to extract the network information to the precision of number of nodes in each. So then there is data poisoning, where the training data is can be poisoned with incorrect labels or data. So precisely that the trained model, it will fail to detect certain classes or certain data from an individual class. Or it can be like, if you know the training data of the model, then introducing a certain type of amount of noise would make the model fail the detection itself. So finally, you will end up with a model that can maybe test the validation and testing phases, but when you put it out in production, so it will fail to detect certain types of adversarial data. And finally, there can be model poisoning also, which can be achieved by disturbing the parameters, or by tampering with the learned parameters, which can actually degrade the accuracy of the model, or even make the model non-responsive, denial of service situation. So why we need a standard approach for AI development is because that would open doors to evaluation. And since nowadays we have custom AI implementations everywhere, and there is no design guidelines or a generic implementation guide for AI development on hardware, it is very difficult to perform any kind of evaluation. So it's especially difficult to do vulnerability assessment and therefore to prescribe precise countermeasures. So finally coming to the end of the presentation. So a solution to this problem that we have proposed is the use of a hardware security module to work as a wrapper to the machine learning model, which protects its integrity and communication. So for our case, we have digital sensors spread across the chip surface and the machine learning computation engine that performs the detection. So the digital sensors are placed for detecting abnormalities, so they do not need to be protected as such. But a machine learning model can be placed inside an integrated secure element, which also protects the communication channel between the sensor and the machine learning core. So it is understandable that this brings with itself an added overhead, but that is the price to pay for such protection. So in the AI over-the-top security layers, the most important parameters to protect are the learned features and patterns by the AI or the machine learning model during the training phase. So depending upon the use case, the model will learn or not learn after tape out. So in any case, the transactions are needed to be carried out in a secure environment without leaking any sensitive information. So the integrated secure element will make sure that all the AI parameters are safely stored and moved around inside the chip, and the computations for the detection is also carried out in a safe environment. So that would bring to the end of this session. So thank you very much for listening. If you have any questions, I think there are 2 questions here.
Thank you very much. We are running out of time, so there are 2 questions in the Q&A. Let's try to cover them very quickly, and then we'll break maybe for 5 minutes. The first question is assuming that somebody is interested only in the detection, and the question is, what is the added value of the machine learning in that case?
So as I said, the most important step, of course, is the detection. So here, if we are using just one sensor, then that is not enough, because in that case, you can pinpoint some blind spots and then you can perform an attack, and there will not be any kind of detection. So that's why we use an aggregated approach where we use a fleet of digital sensors. And then we will need some way to aggregate these values, and then marking a threshold value for each sensor that would be very, very not feasible. So what machine learning will help in that is aggregating all this data and then do the detection. So that is the first step. So having any kind of attack being targeted on the device, it will try to compare it against a normal chip behavior and give you an output. So of course, that is the most important thing. And then on top of that, if you need for forensics purpose, if you want to classify based on like what kind of attack was targeted, so then you can of course go for the stage 2.
Thank you. The last question is that there's a question about the digital sensors, and the question is what kind of parameters do they send from your perspective?
Digital sensor data. So basically, I think you were talking about information. So it's a 32-bit data, which is generated every continuously from each sensor. So it's like a 32-bit data, one single vector, and it is stored in a buffer which is associated with each sensor. So there is a buffer of, for example, in our case, we used a 13 size of the buffer. So there will be 13 statuses. Each status will be a 32-bit vector, and this is what we aggregate from all the sensors, and that's what we feed in the machine learning model. I hope I answered this question.
Yeah. Okay. I also have a few questions, but maybe I'll ask you privately because we are running out of time. So thank you very much. I appreciate this was an excellent talk. Very interesting. By the way, can you post also a list of publications that you have on this topic? Because you mentioned quite a few, and I think that in the slides you don't have any references. So if you can add references of a publication to the slide,
I will send you.
It would be great. Thank you.
I will do that. Thank you.
So I suggest maybe we'll take a